The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so let's go ahead and proceed with vehicle scheduling. What we try to do in vehicle scheduling, given that up to this point we have frequencies determined for different routes, identify to deliver the service that is specified on the timetable, and then vehicle scheduling, which is the main part, is basically how we are using the existing fleet to deliver the service that is specified on the timetable. How we are basically defining the duties for vehicles from the time that they pull out from depot till the time that they pull back in to the depot again. What is the sequences of the revenue trips or revenue movements, and where that involve deadhead arcs, layover arcs, and etc. We will discuss this in this lecture, and we will get to that. So the task of developing the timetable is basically the task of translating frequencies into a timetable. We may all be familiar with what a bus service or a train service timetable is. It basically includes the list of departures and arrivals to different stops by different routes. There are alternative ways of determining the timetable. The simplest way is to just use equal headways. And the frequency that you allocated to the route at the time period, during the time period, just distribute them evenly over the time period. If you look at the figure on bottom left here, we have an example of even headways here. However, if the demand is not uniformly distributed during the period, for which the example could be peak of peak, that is usually happening, depending on the network, it may vary, but usually happens between 7 and 8, 7:30 and 8:30. Then you may want to work out the headways and work out the timetable in a way to result in balanced loads and equal loads. So in order to do this, what you need to do is to generate the cumulative passenger flow arrivals, and then if you distribute your headways on the time axis, you will get even headways or equal headway service. If you distribute your headways on the cumulative passenger flow evenly, then you would get balanced loads. As you can see, the headways, which is here, 1, 2, 3, 4, 5, balancing loads for timetable development. The other alternative way of developing timetables would be trying to design a clock-based service. Why would we want to design a clock-based timetable? Does anyone have any suggestion? Why? Yep.
Sometimes it makes scheduling easier. If we have some sort of cyclical pattern, it's easier to assign drivers that way.
Right. Yeah. Yes. So that is actually one reason. It may eventually, in the next step, which is crew scheduling, makes the service more efficient and cost efficient. Is there any other? Yep.
It's easier for the passengers to remember the schedule.
Exactly. If the waiting time estimations that we are doing with respect to frequencies and with respect to headways, if passengers are able to coordinate with the service, the expected waiting time would be less than the situation where they cannot coordinate with the service. That's only the case when headway is 10, 15, 20, 30 or minutes or 60 minutes. And then we would have like service every, on minute 1, for example, that would be 7:1, 7:11, 7:21, and so on and so forth. So it's easier for passengers to remember the service that is designed clock face. So again, for the two approaches to headway distribution, equal headway distribution is basically as it can be imagined, each headway would be computed as calculated as peak period duration divided by number of vehicles or frequency that we determined for the route at the time period. And in terms of balanced load solution, we basically need to first realize what the loads are, the balanced loads are by dividing the passenger flows to n, and then work out on the cumulative passenger distribution, cumulative passenger arrivals to realize what the timetable arrivals and departures are. Is there any questions about this?
Yeah. Looking at the graph on the left, if let's say PE4 minus P is greater than the capacity of a bus, then we have a problem. Because if the number of passengers there is a problem with the clock-based.
Mm-hmm. Yeah, that's. However, what we basically did in previous step was in frequency determination. That's one of the checks that we do, the maximum load. And we basically make sure that maximum load is within the allowed standards.
But basically, so what we're saying is, if we do clock-based, then we look where we have the maximum flow of passengers and take that headway and replicate that headway all across the rest of the time period is what you're saying, if I understand correctly. I'm saying I have to design the headway to serve the maximum, and then the rest of the time period, which has lower flows, will have excess capacity.
Right. Yeah. So yeah, that makes sense. It really depends. If we design based on the time period, and we distribute the frequencies evenly, and make sure that we are checking the requirements that are related to maximum load factors, then we won't have any problems. However, the other issue that could actually be the counterpart of the issue that you suggested is that when we're designing the timetable based on balanced load solution, we may actually end up having to use more vehicles required for that solution. And the reason for that, does anyone have any suggestions what the reason for be if the number, why the number of vehicles that we may want to require for balanced load could be?
If you have a peak right at a certain time, the vehicle will only be able to make one trip, and then you'll be sending out a bus just to make a single trip and go back, which adds a lot of deadhead time on either end. Right.
Yeah. So that could be one reason. The other reason would be if we have a peak in our passenger arrivals, then we would have really short time intervals or short headways during peak of the peak, and rather longer headways during the off-peak. And then what happens is that if these longer headways exceed the maximum headway that is allowed, then we would have to basically throw in more vehicles to make sure that we do not exceed the maximum headway allowed, which is one of the considerations related to maximum waiting time for passengers and level of service. So that's one of the issues. So as a result, in general, it is better to assume that design of timetable is going to be based on equal headways, and when we do the frequency computations, be consistent with that.
So, like the statement here that says more vehicles might be required for a balanced load solution, this is applicable only if the vehicles can't be repurposed to a different route, and they are like strictly bound to follow the route that they are set on. Is that valid?
I'm not sure I understand your comment. Can you repeat that, please?
There's a route on which the peak demand is high.
Right.
And if I then allocate based on balanced load solution, then the number of vehicles is going to go up. But since the number of vehicles required during off-peak conditions will be lower, then it necessarily does not mean that the vehicles will go up across the day. It only means that we need more vehicles during certain time periods of the day.
Right.
Just like, I have a question. Why do you think that the balanced load will require more vehicles? I tend to believe that it's actually somewhat more efficient, capacity-wise than the alternative. But why do you think that it has more vehicles?
Because the frequency is higher. So.
Right.
It's higher only at certain points. It's higher only
You have to have enough vehicles to cover however many simultaneous trips.
But what Ian was saying is you can't cut service so short that you don't meet those load factors. So in the end, you end up using more vehicles.
So the reason that we would basically require more vehicles in balanced load is that for some of these headways, we need to stretch the headway in a way that it basically meets the balanced load on the other headways, right? And then once we do that, we may actually go over the maximum allowed headway that is basically trying to take care of maximum waiting time and level of service in the end. In that case, then we need to throw in more vehicles during the same period of the route. And if we need to do this for all the routes at the same time, then we would eventually observe more deficit and more vehicles to be used. Is this the point that you tried to?
Yes, but yeah, my point was more regarding the network, so it would also depend on the network. So if the buses can be used in other routes as well, so one bus that is operating on a given route can be repurposed and used in another route.
Right.
Then it would strongly depend on the network's characteristics in the end.
On reverse?
The vehicle actually goes up or ends up here. And the other thing headway is the deciding factor and the level of service is decided by the minimum headway requirement, then why does load factor in this framework?
Right. Well, these are two different factors, and both are important in terms of level of service. Headway consideration is related to maximum waiting time. You don't want to have like really long headways that would force people to wait longer. And at the same time, you don't want buses that are overcrowded and there's discomfort of resulting from the crowding effect, right? So these are two different sources of disutility, basically, in the service that we try to balance somehow, right? The other issue that you brought up first in terms of the fact that the service may be directional and demand may be directional during peak, and there could be possibility of using vehicles in other directions or using deadheading and situations like that. We are actually going to cover that, and that's true for both of the two scenarios, right?
It seems like there should be some kind of hybrid way to say this is the amount of vehicles I want to use, and there's a way to not have to build your schedule based on equal headways and still
Right, yeah.
Demand.
Exactly, yeah. And so there's all sorts of tricks at these steps where you tweak some of the solutions from one level and go back to the previous levels and adjust those. There's all sorts of engineering judgments and planning judgments that are involved and can actually take place. We will see a couple of those in this lecture too. Okay, so let's go. So now, once we know what the timetable is, the sequence of arrivals and departures for different trips for all routes, then it's a matter of determining what's the fleet size that is required for delivering the service that is timetabled. There's this famous theorem in the literature that deals with an estimation of number of fleet that is required. It is basically an upper bound to the number of vehicles that are required to deliver the service. The reason that it's an upper bound is that it basically assumes that we are going to stick to the original timetable, and we are not allowed to do any trip shifting, or we are not doing any trip shifting in this step to accommodate some of that are 1 or 2 minutes or a few minutes basically conflicting. And then the other assumption that is made here to compute the upper bound of fleet size is that we are not allowing deadheading trips to balance the deficit among the terminals. So let's start with the definitions. The function L of K, T, and S. K is the index of terminal. T is the index of time, and S is the index of schedule that is already developed. So L is basically the cumulative number of departures from terminal by time T following the schedule. And A would be the cumulative number of arrivals at terminal K by time T following that schedule. Then we define a function which is the difference between the two. It's basically the deficit function, which is the cumulative departures minus cumulative arrivals. We use this deficit function to estimate what's the required to deliver the service. So the fleet size theorem says that if we basically compute the maximum number of deficit over all time intervals for each terminal, and we add those up, we will get the total number that is required, number of vehicles that is required to deliver the service. So it's basically this equation, the summation over all terminals, maximum over T of the deficit function. So in this figure, we basically, on top, we see different trips that are scheduled. And each trip is basically identified with a number and a pair of terminals that, for example, trip 1 starts from terminal M and ends at terminal U. And then, as you can see, these trips all start at terminal M. Some of them go to U, some of them go to V, and there's also trips between U and V, and basically some of them come back to M again. So if we basically work out the deficit function for terminal M, what we see is that, for example, at time around 5 a.m., we will have one trip scheduled here, trip number 6. And at 6, there's another one. Our deficit is basically growing until at noon, where the first trip comes back to terminal M. And then at that point, it continues at deficit level 3, where there is one departure and one arrival scheduled at 15, at 17, at 5 p.m. And then it continues until the last trip arrivals at a little bit before 10 p.m. So in this case, if we look at the maximum deficit over time for this terminal, it would be 4. And that's for terminal M. When we look at all terminals in the network and sum up the maximum deficits, the summation will give us number of fleet that is required. However, there are a couple tricks that we can basically improve the efficiency. One of the tricks would be shifting the departures or arrivals a little bit so we accommodate more trips, number of vehicles that are required. For example, in this case, like the deficit part that actually gets to level 4 is as the result of trip 9 being scheduled at around like 11:15 or so. If we can manage to shift trip 9 a little bit forward up to noon, then we may actually get rid of the fourth unit of deficit here and make the total deficit or maximum deficit here equal to 3. There's also the issue of reliability that we may want to consider for these trip arrivals and departures. For example, if you look at this point here where trip 2 arrives, and it's basically based on this method, it is going to be assigned to trip 8. However, what if trip 2 is late by a few minutes? Can we what should we do in that case? Are we going to delay trip 8 to accommodate that? One way of looking at this is that instead of working out the deficit functions with trip times and scheduled trips, we can work it out with half cycles that already includes layovers and 95 percentiles at the terminus to make sure that we kind of have a leeway at the terminals. That will definitely require and result in higher deficits. But again, if we are allowed to shift the trips a little bit back and forth, then that's something that would be recommended, to work with half cycles instead of working with the scheduled trips. Is there any questions about fleet size required computation here? Okay.
So do agencies use the shifting technique to reduce fleet size deficits? Do they actually employ the techniques of shifting?
Yeah, of course. That's a part in timetable. Well, it's going back to one of the steps that was already decided and optimized in the past. But there are all sorts of these revisiting that is going on in transit agencies. Because we do not optimize all the components in an integrated manner all at the same time, and we are basically do a sequential optimization, there's always this requirement to go back to some of those decisions that you thought were optimal at the upper level and adjust those to account for gains in the lower level.
Right, because I assume, suppose that this graph here represents an entire agency, and we'll reduce that agency's fleet size from 4 to 3, saving money on another bus. I mean, that's a lot of money in savings by not having that fourth bus.
Right. Yeah. Well, it's
Do they look at this?
when they design timetables, they try to have some sort of coordination with arrivals and departures. to the terminals. There's an example at the end of this lecture that we're going to talk about how you can coordinate back and forth trips so it will result in lower deficit in the first place. But yeah, sometimes it actually may actually be at the level of fleet size determination. Then you do this these shiftings again to improve the efficiency. Okay, any other questions? All right, a little bit faster on these parts. So when it comes to matter of vehicle scheduling problem, it is a very interesting problem to optimize. The objective of this problem is to define vehicle blocks or sequence of duties for vehicles that includes revenue trips and non-revenue trips. In other words, deadheads to rebalance or to balance the deficit at terminals, or layovers that would actually take place for reliability considerations. So the objective is basically to define these vehicle blocks, given that we are going to cover all the trips that are already scheduled, in a way to minimize the fleet size as a measure of the capital cost and minimize the non-revenue time and mileage. As a measure of a non-revenue time could actually account for crew cost, and mileage could account for both crew cost and fuel and basically operational cost. One important observation is that these are proxies for cost. Again, in the next step of the work, when we are doing the scheduling for crew, we will realize some of the cost actually depends on how these vehicle blocks are defined, and probably the most important components of cost that are related to crew duties are going to be determined in that stage. So these are only proxies for cost, fleet size and non-revenue time and mileages. Input into the vehicle scheduling problem would be of vehicle revenue trips, which is the timetable that we are deliver. Each is characterized by trip stop time and end time and point. Then the other input would be possible layover arcs to account for reliability of these trips and delayed trips. And then deadhead arcs connecting depots to trip starting points. We call those pull out arcs from depot. And then pull ins back into depot from trip end points to depots. And then the deadhead or balancing deficit arcs, these are basically trips that bring vehicles from terminals with lower deficit than what is scheduled to terminals with higher deficit. So what we try to do is that from these arcs, we basically need to choose the optimal combination of these arcs to deliver the service and bring our vehicles out from depot and the same number back to depot again after the day is over. So another important observation or quick note here is that there may be many possible number of deadhead and layover arcs. It's actually from a combinatorial nature. However, the designer or the person who tries to solve this problem needs to review these arcs and come up with feasible and plausible arcs to start with. And then, as I mentioned, the layover arcs are also important in terms of making sure we will have a certain level of reliability. There are variations to the problem that actually can make the problem more complicated, but we are going to stick to the simplest one and show how we can formulate the problem, model it, and what are the algorithms that can solve it for us. These variations basically are related to, one possible variation is related to vehicles servicing single lines or single routes or interlining between different routes. The other variation would be related to possibility of having multiple depots in the network. Larger transit agencies usually have multiple depots. For example, for Boston, I know a few of those. I do not know what's the exact number of depots that exist in the network. Alfred Street is one.
Albany, Southampton, 2 at Bennett, Lynn, Fellsway, North Cambridge.
That's, yeah, okay.
And
So
Parkway.
it's almost close to 10, 9, 8, 9, okay. So when it comes to different depots and having multiple depots, there will be more complexities introduced to the problem, because you may want to make sure that the exact number of vehicles who depart a depot come back to depot. There are also some considerations related to the fuel that the fleet is using. You may have diesel buses, you may have CNG buses. You may want to, if you have restrictions in terms of fueling facilities in these depots, you may want to return back the vehicles to the particular depots that are consistent with the fueling system. Then, so yeah, there are different considerations related to vehicle types, related to parking spaces at the depots, and that actually makes the problem more complicated, but we can actually make some simplifying assumptions for now and see how the problem looks like in the most basic form. So this is the time-space network representation of the vehicle scheduling problem. We are trying, in the next 3 slides, we're trying to build on the time-space network structure to realize what is the decision that we're trying to make and how we can basically solve this. So this is time-space representation with x-axis being time of day and y-axis being a space. This is only one-dimensional space here, but it could be two-dimensional space too. So in this case, we have like 2 routes that are represented here, route 1, or n routes, route 1 to route n. As you can see, there are trips from either direction of these routes that are already timetabled, and we have already committed to deliver this service. So the black arcs here are revenue arcs that are the arcs that we committed, and these have to be delivered between the 2 terminals of every route. Then we have, in this problem, we have only 1 depot. There are 2 nodes here that are represented as depot, but it's basically the representation of depot at the beginning of the day when vehicles pull out, and the representation at the end of the day when vehicles pull in, basically. There are also layover arcs where you connect all possible alternatives that you may think would be plausible for connecting these trips to one another. So in this figure, we only have a few of those, probably the closest one, but you can work out any possible combination of bus arrival to a terminal being connected to a different trip from that terminal.
Would you mind explaining what this figure means a bit more? Maybe I'm missing something. Like, for example, when we start out at the beginning of the day,
Right.
Let's say out 1.
Right.
We have 2 lines emanating from the very beginning of the day.
Right.
So is that 2 buses leaving the depot at the same time? Maybe slightly different time?
Right. Yeah. So let me go ahead and continue and finish all the arcs in the network. That may clarify the situation a little bit, because there are other arcs in the network too.
Okay.
So there are arcs that are pull out arcs from the depot to these to start these trips, and arcs that return the vehicles back to the depot. There's also arcs that are there to account for possibilities of deadheading trips. from one route to another route.
Okay, so now we have those two nodes going into Route 1. So two buses going into Route 1, right?
These, that's only a link. That link may include multiple vehicles, right?
Okay.
Multiple vehicles.
Multiple vehicles at different times?
Multiple vehicles
Yeah.
at different times.
There's probably like this.
Well, it could be. Yeah. Let me. This is not the exact representation of time-dependent service. You can actually have connections if you consider each one of these links to carry only one vehicle or not. Then you need to add vehicles from depot to other trips along the time dimension too. Vehicles that are basically joining that route at your time.
And what is the top?
The top line, you can.
It's like they're
Top line is just.
So we're sending buses from the depot to the end to start.
It could be. Yeah. This is right. This is again a simplified situation, but you can pull out at the middle of the route too, where you can, for example, just serve a vehicle from here. But you may want to make sure that the scheduled trip is served. So if you have services that basically start from the middle of the line, then you can model that too. This is just to show how you can model a situation like this. It may not be all comprehensive combinations or situations.
I just wanted to make sure I understand what it says.
Does it make sense now?
Yeah, I think so.
Okay, good.
I think one of the confusing things about this model actually is that you have that horizontal line.
Right.
It's saying that the same color as revenue. Really what you should have is you should just have that layover arc shouldn't be an arc. It should just be a line connecting the end of one of the...
Exactly, yeah. These horizontal lines, I should actually remove that. I will.
Yeah, and then
Yeah.
just make the layover arcs lines.
Yeah, exactly. Layover arcs. That's exactly true. Yeah. Actually, make the connection between the two directions of the route, and then the other arcs that are involved are the deadhead arcs, points in the network.
It should be noted that the layer arcs are not really. I mean, they're just. There's no spatial dimension to them because the bus isn't moving.
Right, yeah, exactly. Maybe that's the only special dimension to it would be just go ahead and turn around over the corner.
Yeah,
and then come back, yeah.
The case that the bus that pulls into the terminal is the next one out. So that's when you might actually want to have the arc to show that even though it's not really moving.
Right,
Actually,
yeah.
There is a reason why you might want to show it that way.
Exactly. And then the other point is that this is like even from this node to nodes further down. The reason that we are think the optimization problem in the network structure, like many other optimization problems, is that with networks that consists of nodes and arcs, we can represent the constraints very efficiently. And there are efficient algorithms that use this representation to solve the optimization problem. So whenever we can present an optimization problem in a network structure, we do that because we have really elegant algorithms in network flows that can be used to solve optimization problems. So let's see what's the optimization problem to solve here. One other link that we need to add here is basically from depot to depot to make sure that the total number of vehicles that are going out of the depot in the morning are going to be equal to the total number of vehicles that are coming back to depot.
So we're assuming, just to go back to that, there are some lines there that don't have a pull-out. We're assuming those are coming from other depots.
Yeah, in this example, we're only simplifying it into one depot situation.
Right.
But some of the, exactly. Some of the other routes could actually be.
The question is for route N, the first one that's going from the bottom to the top doesn't have a pull-out, so there should be an arrow going to that.
There should be an arrow, yeah, to that too. But it's missing in this, yeah.
Okay.
These arrows are only representative, and they're not, yeah. comprehensive. And we basically are defining integer capacities that would reflect number of vehicles that are doing that duty or are basically assigned to those duties. These arcs are revenue, layover, and deadhead arcs. And these arcs, again, have costs. Like revenue arcs have given amount of cost depending on the time that they take to make the trip, and so on and so forth. Layover trips, depending on how much time they take, and deadhead arcs, depending on how much time they take and how much mileage they require to travel the vehicles. However, what's interesting is that the reverse arcs costs of 0 for those because it's not relevant. We eventually would have to deliver those revenue arc services. So it's a constant in the optimization problem. We might as well just remove them. But what's important is that we want to see what the layovers, what's the optimal combination of layovers and deadheads in this problem. So again, the bounds that we have for revenue arcs is basically lower bound is 1, upper bound is 1. Why is it like this? Does anyone have any suggestion why the lower bound and upper bound are both equal to 1 for revenue arcs?
You said we have to operate those trips no matter what.
And we only have to operate to deliver them once, right? Yeah. Remember, these are trips in the time-space representation. So each trip is basically one arc. We need to deliver it once. So it's basically the matter of choosing all configuration of layover arcs between 0 and 1 and deadhead arcs between 0 and 1. A maximum block length is guaranteed. This is usually not a problem if the fuel situation, especially for electric vehicles, is restricting. We may want to put additional restrictions on maximum length of the vehicle. But with the existing diesel and CNG vehicles, these are usually fine to deliver the whole service day services without having to refuel. Interlining is something that is already taken care of in the vehicle scheduling problem. However, shifting heuristic needs to take place before we get to vehicle scheduling at the level of timetable development, as we discussed after the deficit functions. So the matter would be if we have multiple depot, the problem becomes a little bit more complicated. For single depot situation, we can solve the problem with network flow algorithms, minimum cost flow algorithm that is very efficient and very fast. When it comes to commodity flow with integer, which is the case in the problem that we have, then the problem becomes really difficult. It becomes NP hard, and it basically is very difficult to scale. That basically means that we do not use the network flow algorithms for multi-depot situation. We use some of the existing heuristics. Is there any questions about this so far? So this is another network representation of the multi-depot vehicle scheduling problem. This is not a time-space representation anymore because it would become really complicated with time-space representation. As you can see, there are different depots in the network, and there are different services that need to actually, or revenue arcs that need to be served. There may be some constraints on number of vehicles that pull out from each one of these depots and pull in each one of these depots. And again, if we didn't have the constraint of having integer solution, this could be solved in linear time too. However, with integer constraints, it's not possible. Okay, so is there any questions about this? It basically, in order to be able to implement this, we need to make a definition on trips and identify compatible trips. Two compatible trips at the terminal, I and j, two trips I and j are compatible at the terminal if j is arriving to terminal, I is departing from terminal, and the time difference between the two is actually greater than the layover that we want, and then also less than twice the time of traveling from depot. The solution may be only as good as just sending the vehicle back to depot and then pull it out from depot to another part of the network. So we only restrict the search for compatible trips to these two bounds. Like MK here is the minimum recovery time that we define as a lower bound of time difference between the arrival of trip I minus departure of trip J. And then we use 2 times dk, which is the deadhead time from terminal to depot. Then the algorithm is really simple. It has only 4 steps. We start with the earliest arrival at terminal. If there's no earliest arrival, we go to step D, and basically in step D, we need to pull out from depot to serve that service. But if there is one earliest arrival, then we link that earliest arrival to compatible trip departure based on the compatibility constraint or definition that we had. Again, if there's no trips that is compatible with that, we need to go back to step A and basically use the next arrival at terminal. If there is one trip that is compatible with the trip that arrives, then we will check the vehicle block length against the existing constraint. Again, that could actually be related to the fuel and fueling constraint and so on and so forth. If it's constraining, then we need to cancel that and return the vehicle to depot. Otherwise, we would basically make the connection between the compatible trips and consider the second trip a new arrival to the other to the downstream station, basically. After that, we sell again all remaining on-link trips from depot. You need to work out in your mind these steps once. Very easy practice to realize how this works. But it's basically using the strict first in, first out rule based on compatibility of trips and over the compatible trips. Is there any question? Yeah.
Can kind of come back a little bit?
Uh-huh.
You said that when on the single depot, it's like why?
For single depot situation, the existing algorithms that solve minimum cost flow, like successive shortest path algorithm or some of the negative cycle canceling algorithms, can give you integer solution. However, when it comes to multi-depot and when it comes to multi-commodity flow, that's not always true. So you may actually get a solution with a linear or with a network flow algorithm that is in linear time, but it's not integer. So you may have decimal or partial vehicles going back to different depots. That's the difference between the two cases. Okay. So other questions? All right. So after this, we just will have just one single route scheduling practice with 2 nodes, A and B, or with 2 terminals, A and B. this is one route that we want to schedule for AM peak period and base period. AM peak is defined from 6 to 9, and base period is after 9. Headways are during peak period 20 minutes, and scheduled trip times are 40 minutes for both directions. Layover is 10. During off-peak, headways are 30. Scheduled trip time is 35, and minimum layover is, again, 10. Dominant direction of travel is AM peak, and it's in the direction of A to B. So then what we do is that we will direction A to B, and given the headways and running times, we work out for all the trips that are scheduled during peak from 6 to 9, and then after that up to 11, and the rest could be actually similar. So as you can see, the headways from 6 to 9 are 20 minutes. After that becomes 30 minutes. The in-vehicle time, or the running time, is 40 minutes in the peak and 35. The first thing that we do is that we tie the two directions together. This is the kind of coordination that we previously discussed with the comment that Eitan made in terms of shifting these trips together. So this is one of the one example of shifting some of the trips to make better efficiency in the next steps. In this case, we tie the trips in the first direction with trips in the reverse direction. So first trip that departs at 6 arrives at 6:40. Considering 10 minutes layover, we will schedule the first trip for the reverse direction from 6:50, and it's anticipated to arrive at 7:30. And this is so on and so forth for all the timetable, given the time in, the travel times between the two ends and the headways.
Which means we need 5 buses?
Yes. Yeah. But we'll work this. Right. We need 5 buses, but some of them are partial only. They can pull in the middle and pull out, but we will see that in a second. So we will start with first pull out. That is the bus that is going to serve the first round trip. After one cycle, is going to be able to serve the 7:40 trip for us after 10 minutes of layover. It will end the trip at 9:10. Given 10 minutes layover, it will be able to serve 9:30 for us, and also 11 again. The next bus that we will have to pull out can serve the trip from 6:20, and from 8. After 8, once it does the cycle, it's going to be 9:30, and 9:30 is already trip is already taken. Then we will have to choose between sending this back to the depot or using it for trip at 10. This trip at 10 basically means like 30 more minutes or 20 minutes of waiting. We decide to send it back to depot. We will have 5 blocks for 5 different buses. Block 1 basically gives the itinerary of duties for bus 1 or for whichever bus that this is assigned to. Then so on and so forth for all the buses. Okay, you mainly will have to work with this method for the homework, but it's valuable to know what are the existing approaches in practice and what's going on in research that deals with problems like this. Okay. Any questions? All right. Okay. Thank you very much.